Okay, this lesson is on force as a vector quantity. Our learning goal is that we're learning to find the net force acting on an object by finding the vector sum of all forces acting on the object. Okay, so sum adding, so we're adding the vectors together and finding the resultant, and that's going to be called the net force. According to Newton's law, an unbalanced force causes an object to accelerate. Newton's first law of motion states that an object will remain at rest or in uniform motion unless it is acted upon by an unbalanced force. It's Newton's first law. The net force, which is what we're going to be finding, acting on an object is the vector sum of all forces. Force is measured in units called newtons, and the symbol for newtons is capital N if you haven't taken physics before. And that's okay, you just have to remember to use newtons when you're talking about units of force. So question 1, determine the net force. And notice the symbol we use. We use a lowercase f, so if you have taken physics, you may be used to using an uppercase f, but in vector algebra, we always use just one lowercase letter with a vector symbol over top, or two uppercase to denote a point to point. So we're going to be using small f net here. Determine the net force acting on each object. So here's our object. It's represented by a dot here. And we've got this up, down, right, left compass system here. So we can see that this object, if I redraw it over here, it's being pulled up by a 1.5 Newton force and down by a 3 Newton force. So if we just look at up and down, the net up and down would be 1.5 newtons down. So I'm going to draw that right now. 1.5 newtons down. And then if we just looked at the left and right, 3 newtons to the left cancels out 3 newtons to the right. So I'd just be left with 2 newtons to the right. And I want to add that on to the tip of the first vector because you add vectors tip to tail. So this is going to be 2 newtons to the right. And then my resultant F net is going to be from the tail of the first vector to the tip of the second vector. Make sure you show your arrow carefully. And then label this one as small f net with an arrow over top. Here's my vector. And we know that down and right make a right angle, 90-degree angle with each other, so we can just find the magnitude of F net. So remember, use absolute value bars when you're finding the magnitude of a force. And we can just use the Pythagorean theorem because it's a right triangle. So the magnitude of F net squared, and F net's the hypotenuse, is going to be 1.5 squared plus 2 squared. And then the magnitude of F net then is going to be the square root. So the square root of 1.5 squared plus 2 squared is 2.5 exactly. So we don't need an approximate sign there. So the magnitude of the force is approximately 2.5 newtons. But we also need direction because force is a vector. So there's our magnitude. Our direction, we can see if this is F net here, is going to be down and then so many degrees towards the right. So this is theta in here, our angle. And because this is a right triangle, we can use like hypotenuse, this is the opposite, and this is the adjacent according to angle theta. So I can use tan. Tan of theta is opposite, which is 2, over adjacent, which is 1.5. Theta is the tan inverse of 2 over 1.5, or approximately 53 degrees. So then we're going to put our magnitude and direction together, our therefore statement. So therefore F net vector, no magnitude bars anymore, is approximately, even though the magnitude turned out to be a perfect number. Our direction is not, so our overall vector is approximate. So F net is approximately 2.5 newtons, and then this direction here would be down 53 degrees towards the right. So there's F net. So our second problem, again, shows an object portrayed by a dot here, and it's being pulled by a 10 Newton force to the east and by a 14 Newton force to the northeast. And remembering northeast means north 45 degrees east. So again, right now those vectors are tail to tail, and also we know that that angle in there is 45 degrees. But when we add them, we have to add them tip to tail. So I'm going to take this vector and add it to the tip of this one. So I want to make it look like it's at the same angle and the same length. Arrow on the end. Label it. So this is a 14 Newton force in the direction northeast, or north 45 degrees east. And then I'm going to draw in my net force, which goes from the tail of the first to the tip of the second. Make sure you exaggerate that arrow there, and then label it F net, small f net. And then because these are parallel, we can use the C pattern where these two angles add up to 180. So this angle in here, which looks obtuse, is 180 minus 45 degrees, which is 135 degrees. So because we know that angle and the magnitudes of these two sides, we have enough information to use the cosine law to find the magnitude of the force. So the magnitude of F net squared, according to the cosine law, is equal to 10 squared plus 14 squared minus 2 times 10 times 14 times the cosine of 135 degrees. And then we can find F net on our calculator. I'm going to do square root of, because I know I'd have to square root this side to get from F net squared to just F net. 10 squared plus 14 squared minus 2 times 10 times 14 times the cosine of 135. Closing bracket gives me approximately 22.2 newtons. Remember, the units of force are newtons. But net force has a magnitude and direction, and we can see the direction's going to be in here. So it's going to be east so many degrees towards the north. So we'll find theta. So we can use the sine law because theta is not going to end up being the largest angle, though 135 is. So sine law, sine of theta over the opposite side, which is 14, or the magnitude of the opposite side, is equal to the sine of the angle we know, 135 degrees, over the magnitude of F net, which we have on our calculator, is approximately 22, I could say 0.2259. And then theta, if you multiply both sides by 14 and take the sine inverse, it's going to be the sine inverse of 14 times the sine of 135 degrees over 22.2259. You can show that step if you want to, but in grade 12 it's okay just to go from this step to this step. So theta is approximately, so we want to do sine inverse of 14 times the sine of 135 degrees divided by 22.2259. And my angle is at 26.449, so I'm going to say approximately 26 degrees. Round angles to the nearest degree. And then we have to do our therefore. So we're finding net force. So therefore F net without the absolute value, because we're not just stating the magnitude, we're stating it the magnitude and direction. So it's approximately 22.2 newtons in the direction east first, and then 26 degrees towards north. And for C, we've got, this is our compass, so we're doing up, down, forwards, backwards. This 160 newtons is forwards. And you can see this 240 Newton force would be in a direction of forwards, 52 degrees up. And we want to find the net force acting on this object. So again, we're going to move the 240 Newton vector so its tail is at the tip of the first vector here. Again, make it look parallel and the same length. And then we want to draw in the net force. I'll label this one. So this is 240 newtons forwards, 52 degrees up. And our net force is from the tail of the first to the tip of the second. Arrow, and then F net. Okay, and again, these are parallel. So this angle in here that we need is 180 minus 52. So 180 minus 52 is 128 degrees. And again, we can use the cosine law. So we can find the magnitude of F net squared using the cosine law. So it's going to be 160 squared plus 240 squared minus 2 times 160 times 240 times the cosine of 128 degrees. Then I go to my calculator and find out the magnitude of F net approximately. Remember to make sure your calculator is in degrees. And then square root, approximately 361.2 newtons is my net force. And then I also need the angle, and the angle I'd be interested in is from forwards to F net. There's my theta in there. So sine of theta divided by the magnitude, so this vector, which is 240 newtons, is equal to the sine of 128 degrees over 361.224. And again, theta will be the sine inverse of, so theta is the sine inverse of 240 times the sine of 128 divided by 361.224, or approximately 32 degrees. Is that 31.57? And then we'll do our therefore statement. So therefore, F net, the net force, is approximately 361.2 newtons. And the direction is going to be forwards, 32 degrees up. D. A toboggan is being pulled with a force of 70 newtons at an angle of 25 degrees with the ground. What horizontal force is exerted on the toboggan? Okay, so I'm just going to make a dot for my toboggan, and it's being pulled with a force of 70 newtons. That makes an angle of 25 degrees. So let me here's the ground. and 25 degrees. So here's my net force, which we know is 70 newtons. And then my direction is going to be same as it was above here. So we have up, down, forwards, and that would be backwards. So the 70 newtons is going to be, because this is 25 degrees in here, forwards, 25 degrees up. So there's my labeled vector with my arrow. And it's made up of, that net force is made up of a horizontal force, which I'm going to draw here. And I'm going to call that F, small f. And then often for horizontal, you use X as your subscript, because X runs horizontal. Or you could put F horizontal and then with a vertical force added onto it. So this is often called Fy, and then they're at 90 degrees to each other. And the question is asking us what the horizontal force is, or what's Fx. So this is what we're being asked about. With what force is the toboggan being pulled forwards? Okay, so because this is a right triangle, we can use SOHCAHTOA, and this is the angle we know, the 25 degrees. So hypotenuse is going to be involved because we know it's 70, its magnitude is 70, and adjacent is going to be involved because that's what we're trying to find. So we can say that the cosine of 25 degrees is equal to the adjacent, but the magnitude of the adjacent side, over the magnitude of the hypotenuse, which is 70. So then if we multiply both sides by 70, the magnitude of the horizontal force is going to be 70 times the cosine of 25, or approximately 63.4 newtons. But it wants the horizontal force, and force is a vector, so therefore Fx is approximately 63.4 newtons, and we need a direction, and our direction is forwards. Okay? And this is a similar question, only this time we're pushing instead of pulling. So again, I'm going to use a dot for my lawnmower. We're pushing. A lawnmower is pushed with a force of 90 newtons directed along the handle, which makes an angle of 36 degrees with the ground. So I'm going to have my ground, again with a dotted line here. And 36 degrees to it, it's like maybe this. And then here's my arrow because I'm pushing downward. So this vector here is 90 newtons. And then it's made up of, so here's my compass again. So I've got up, down, forwards, and backwards. And we can see that that 90 Newton that we're pushing along the handle has got a vertical component, Fy, that's pushing it towards the ground. And it's also got a horizontal pushing it forwards, Fx. And we know that this is where our 90-degree angle is. So our direction is going to be 90 newtons. And then if you think of our compass being up here, it's going to be forwards. And then there's like a Z pattern here. 36 degrees down is my direction. Remember, make sure you've got arrows on the ends of all your vectors in your vector diagram, really important. So with what force is the lawnmower being pushed forwards? So they want Fx. And again, we have a 90-degree triangle with one angle. So according to this 36 degrees, we know the hypotenuse and the adjacent again. So the cosine of 36 degrees is the magnitude of the horizontal force divided by the 90 Newton force, the magnitude of the hypotenuse. So the magnitude of the horizontal force is approximately 90 times the cos of 36, which is 72.8 newtons. And then again, because we're talking about a force, the horizontal force, therefore, is approximately 72.8 newtons forwards. So again, in your vector diagrams, being very careful to use arrows, labeling them properly. If you know the magnitude and direction, labeling both of those. If you're just using a letter, then a small letter for F, a subscript. And remember, vectors are added tip to tail. Okay, with what force is the sled being pulled forwards? Okay, so here's our sled, here's forwards. So I'm going to make a compass first, since they didn't give me one, so that my answer makes sense here. So if I'm looking from above here, this is my forwards. This is backwards. And this is to the right, if I'm looking down on it. And this is to the left. Okay? So with what force is the sled being pulled forwards with? And you can see that both people are pulling at the exact same strength, 55 newtons, in the exact same direction from forwards. So that means the sled is going to go forwards, but we still want to draw the appropriate vector diagram here. So I'm going to draw forwards here with a dotted line to start out with. And here's my sled. And I know my sled's being pulled with these forces. I'll try to make them look. So they should be the same length. And they're at the same angle, 35 degrees. And this can be F1, and this can be F2. And right now they're tail to tail, but when we add them, it's tip to tail. So we're going to move this one. So it's at the tip of this one. And we know that it's going to land right on straight forwards because we know we're going to end up going straight forward. So this is F1 redrawn here. And we know that the net force is going to be straight forward here because the forces are balanced. Each person's pulling at the same strength at the same angle. So the sled will end up going forwards. So this orange one I've drawn is F net. And we know that these are both have a magnitude of 55 newtons. So if I'm just doing, the magnitudes, put the magnitude bars there. I know my net force is going to end up being forwards. Because this is now an isosceles triangle, because both magnitudes are the same, then this is 35 degrees, we know, because we end up going forwards. This is also 35 degrees. And this angle up here, so we'll know all three angles, is going to be 180 minus 35 minus 35, which is 110. So because we know all three angles, we can use the sine law. Okay, so we can do find the magnitude of F net using the sine law. So the magnitude of F net over the sine of 110 degrees is equal to 55 over the sine of 35 degrees. So multiply both sides by sine 110. and the magnitude of F net. So it's going to be 55 times the sine of 110 degrees divided by the sine of 35 degrees. 90.1 newtons. And we know it's forwards. So with what force is the sled being pulled forwards? Therefore, F net is approximately 90.1 newtons forwards. And because it's kind of a word problem with a picture and everything, we might do also a statement. Therefore, the sled is being pulled forwards with a force of 90.1 newtons. Okay, so again, this question involves a labeled vector diagram with arrows, okay? Are showing our calculations using absolute value bars when needed and not when they're not, stating my vector with a magnitude and direction, and a statement, because it's a word problem. Question 5, person A pulls with a force of 80 newtons. With what force must person B pull so that the sled moves straight forwards? And we're shown person B pulls at an angle of 27 degrees to forwards, and person B with person A, with 58 degrees. So again, I'm going to make my vector diagram. So here's my sled, and then I'm going to draw the horizontal in here. So person A is pulling at 58 degrees. I'm going to make this look similar here, make it look similar length. And person B is, and this is 58 degrees here. And person B is pulling at 27 degrees. But we want the sled to end up going straight forwards, okay? So he's pulling at less of an angle, so he's going to have to pull harder than 80 newtons. And you can see that when you go to draw in your picture here. I'm just going to extend this dotted line because I might need to. And I make this angle look small, parallel. Where do I meet the dotted line? Still going here. Okay, so this is, let's call this FA, because this is person A, and this is person B. And then I'm drawing in, we know forwards is going to be my F net, because I want to end up going straight forwards, and I want to know what magnitude of force person B needs to pull with so that that ends up happening. So again, my two arrows meet. This is F net here. And I know that these are parallel vectors because this is representing the direction of B and this is the force of B, and they're parallel. So this full angle plus that angle has to add up to 180 by the C pattern. So that angle is going to be 180 minus 58 minus 27. So this angle in here is 95 degrees. So that means I know this angle's 95, this angle's 58 in here. So I know 2 out of the 3 angles, which means I actually know all 3 angles. This angle over here is going to be 27 degrees. 180 minus 95 minus 58. And since I know all three angles again, and I know one side, I can find the force that person B has to pull with. So the magnitude of the force that person B has to pull with over the sine of 58 degrees, the angle opposite, is equal to, so the side we know is the 80 Newton force that person A has to pull with over the sine of 27 degrees. And we can multiply both sides by sine of 58 degrees. And we get that the magnitude of the force that person B has to pull with is going to be 80 times the sine of 58 divided by the sine of 27, or 149.4 newtons. And our diagram suggested that that was going to happen because this was at a smaller angle. You were going to have to pull harder for it to end up going forwards. And then we should do a therefore statement. So with what force must person B pull so that the sled moves straight forwards? So therefore, person B must pull with a force of 149.4 newtons. And if we wanted to make a compass, the direction would be forwards. This would be right, and this would be left. So forwards 27 degrees right. It's always better to be safe and always give if you're talking about a force, give a magnitude and a direction, unless it specifically just asks you for the magnitude. Okay, and our last question. So a stranded barge is being pulled by two boats. Boat A pulls at an angle of forward 22 degrees port, and boat B pulls 3 times as hard as boat A at an angle of forwards 10 degrees starboard. What direction does the barge move? Okay, so first of all, let's make our compass. So if this is forwards, then this is back. And this is port, and this is starboard. Leave. I just want to make sure that's right. Sorry guys, I'll just check in on that. Forgot something. I always mix those up, so I just want to make sure that we've got it here. Port, starboard. Okay, so nope, I had them backwards. Good. I'm glad I checked. So if this is the bow, then port and starboard. Yeah, so here's my picture. There, I found on my phone. So here's the bow, forwards. So port is to your left and starboard's to your right. Okay, so we got our compass. So here's our stranded barge. My dot It's being pulled by two, say, tugboats. Boat A pulls at an angle of forwards, 22 degrees port. So let's do our dotted line to represent forwards. So there's boat A pulls at an angle of forwards, 22 degrees port. So here's my boat A. So we'll call that F, capital A, for the force that tugboat A is pulling at. We know that that's 22 degrees here. And boat B pulls 3 times as hard as boat A at an angle of forwards 10 degrees starboard. So 3 times as long, but at just less than half the angle. So something like that is FB. And that's only 10 degrees in there. And then we want to add them. Tip to tail. So I'm going to move this one over until it hits the line here. So this is my FB. And again, these are parallel to each other. And then this forwards. Oh, sorry, no, we don't end up going forwards. We don't know the direction we're going. My bad there. I'm gonna erase that forwards line. Well, not erase it, but just make sure this is the right length. I think it's a bit longer. Okay, so these are the same length now. It is just an estimated length, but our net force, we're not going to end up going forwards. It's asking what direction we will move. So from the tip of force A to the tail of force B is our F net here. So if we found this angle in here and it turned out to be 22 degrees, then the boat would end up going straight forward. If we found that angle out and it was less than 22, this angle here, then between the orange F net and the FA, if we found it and it was less than 22, then it would be going a bit to the port side, and if it was more than 22, it's going to the starboard side. Okay, so that angle that we're going to end up finding here, theta, is what's going to determine the direction the barge moves. And then another piece of information we're given is that boat B pulls 3 times as hard as boat A. So we know that the magnitude of the force that boat B pulls at divided by the magnitude that the force of boat A pulls at is going to be 3/1. Okay? So we could, as long as we keep our forces in that ratio, we could use 300 newtons and 100 newtons, or 3 newtons and 1 newton, as long as we keep that ratio a constant there. So we can find out, we know this angle in here by our C pattern. So since these are parallel, this angle here is going to be 180 minus 22 minus 10, or 148 degrees. Which means we can find the magnitude of the net force first using the cosine law. So the magnitude of the net force squared is going to be the magnitude of FA, which we can say is 1 squared, plus the magnitude of the force of boat B, 3 squared, minus 2 times 1 times 3 times the cosine of 148 degrees. And then carefully put that in our calculator. And we have that F net is approximately 3.88. so approximately 3.9 newtons. But we really want the direction is what the question asks for, so we really want theta here. So sine theta over 3, because that's the magnitude of FB, is equal to, so sine 148 degrees over F net, which we can keep more decimal places to be more accurate here, 3.884. So theta is going to be the sine inverse of 3 times the sine of 148 divided by 3.884. 24.2 or 24 degrees approximately. So again, we said, so this is the angle again between this orange F net force and the FA force. That angle in there is what we're looking at. If it turned out it was 22, then our boat would end up just going straight forwards, right? And we said if it's bigger than 22, then it's gone into the starboard side a bit, but only by 2 degrees we can see that. So what direction does the barge move? So therefore, the barge moves in the direction forwards and only 2 degrees towards starboard side. Forwards 2 degrees towards the starboard side, because angle theta is actually 24 degrees, bigger than 22, so it goes 2 degrees towards the starboard side. Okay, so that's probably the trickiest type of force question. All right.